In the early days of organic chemistry, chemists understood that molecules were made of atoms connected through chemical bonds. However, the three-dimensional shapes of molecules were utterly unclear since they couldn't be observed directly. Molecules were represented using simple connectivity graphs, like the one you see here. It was clear to savvy chemists of the mid-19th century that these flat representations couldn't explain many of their observations, but chemical theory hadn't provided a satisfactory explanation for the three-dimensional structures of molecules. In 1874, the chemist Van't published a remarkable hypothesis. The four bonds of a saturated carbon atom point to the corners of a tetrahedron. It would take over 25 years for the quantum revolution to theoretically validate his hypothesis, but Van't supported his theory using optical rotation. Van't noticed that only compounds containing a central carbon bound to four different atoms or groups rotated plane polarized light. Clearly, there's something unique about this class of compounds. Take a look at the two molecules you see here. Each one is characterized by a central tetrahedral carbon atom bound to four different atoms: bromine, chlorine, fluorine, and hydrogen. We might be tempted to conclude that the two molecules are the same if we just concern ourselves with what they're made of. However, let's see if we can overlay the two molecules perfectly to really prove that they're the same. We have free license to rotate and translate both of the molecules as we wish. Remarkably though, no matter how we move the molecules, we find that perfect superposition is impossible to achieve. Now take a look at your hands. Notice that your two hands have all the same parts: a thumb, fingers, a palm, etc. Like our two molecules under study, both of your hands are made of the same stuff. Furthermore, the distances between stuff in both of your hands are the same. The index finger is next to the middle finger, which is next to the ring finger, etc. The same is true of our hypothetical molecules. All of their internal distances are the same. Despite the similarities between them, your hands and our molecules are certainly not the same. Try superimposing your hands on one another. Just like our molecules from before, you'll find that it can't be done perfectly. Now, point your palms toward one another. Wiggle both of your index fingers. Notice that your left hand looks as if it's looking in a mirror at your right. In other words, your hands are mirror images. The same can be said of our molecules. We can turn them so that one looks at the other as in a mirror. Your hands and our molecules possess a spatial property in common called chirality, or handedness. Chirality means exactly what we've just described. A chiral object is not the same as its mirror image. Chiral objects are very special in both chemistry and everyday life. Screws, for example, are also chiral. That's why we need the terms right-handed and left-handed screws. And believe it or not, certain types of light can behave like chiral screws. Packed into every linear plane polarized beam of light are right-handed and left-handed parts that rotate together to produce plane polarization. Chiral molecules placed in a beam of such light interact differently with the two chiral components. As a result, one component of the light gets temporarily slowed down relative to the other. The effect on the light beam is a rotation of its plane from the original one, otherwise known as optical rotation. Van't and later chemists realized that the chiral nature of tetrahedral carbons can explain this fascinating phenomenon. Chirality is responsible for all kinds of other fascinating effects in chemistry and everyday life. Humans tend to love symmetry, and so if you look around you, you'll find that chiral objects made by humans are rare, but chiral molecules are absolutely everywhere. Phenomena as separate as optical rotation, screwing together furniture, and clapping your hands all involve this intriguing spatial property.